Previously, we looked at how you could fit parameters to a linear equation. And using this, you could have a computer learn over time the best set of parameters to solve that equation. This is the fundamental underpinning of machine learning. And now we'll see how the principle forms the concept of a computational neuron, the building block of a neural network. Earlier, we saw the code that what I like to call the hello world of neural networks, where you'll use a neural network to learn the relationship between a set of X's and Y's. The architecture was a neural network with a single layer, and this contained a single neuron indicated by this line of code, where we have a sequential defined, which only has one entry for the one layer, and that entry has only one unit for the single neuron. So our neural network really looks like this, a single neuron with X in and Y out. After training the neuron to learn the relationship between X and Y, we can then ask it to predict the value of Y for a new X. For example, the Y when X equals 10.0. We know that the relationship between X and Y is Y equals 2X minus 1. And the neuron learns something close to that. When you print the result of model.predict 10.0, you will see something close to 19, but not exactly 19. This will be more like 18.998. To see why, let's look under the hood a little. Revisiting our neuron with X in and Y out, we can say that Y is a function of X. And that function is Y equals WX plus B, the linear equation. So we could redraw our architecture a little bit, thinking in terms of parameters. If Y equals WX plus B, we need to know the values of W and B in order to get Y from X. So how can a computer figure these out? Well, we can start by emulating the neuron. Here we can do so with a class called model. This has initial values W and B. We can initialize them to do anything we want. Say we set them to 10.0 each. The class will also have a function that will return WX plus B for a given X. So for our known set of X's, we'll see what this model can give. As we initialize W and B to 10, Y equals WX plus B will give us this set, where X is minus 1, Y will be 0. Where X is 0, Y will be 10, and so on. This, of course, is very different from the set of Y's we already know. When X is negative 1, Y is supposed to be negative 3, but we got 0. When X is 0, Y is supposed to be negative 1, but we got 10. Indeed, when X is 4, Y is supposed to be 7, but we got 50. We're way off. So recall the paradigm diagram where we make a guess, measure our accuracy, optimize based on this information, and repeat. You could say that at this point with W equals 10 and B equals 10, we have made our first guess. And by comparing our Y's with the expected ones, we can see our accuracy was off. If we want to measure our accuracy, we can create a loss function in code where we give it the predicted Y, which is the set we calculated, and the target Y, which is the set that was supplied. And from there, we calculate the root mean square error for the difference we explained in an earlier lesson. Then this code is our underlying training code. We'll use a gradient tape to keep track of our differential variables. And within it, calculate our loss using the loss function we just saw. The gradient tape essentially records the sequence of operations performed upon the input and producing the outputs, so that it can calculate and keep track of the gradient as we compute our loss with each guess, which we can see here. Our current loss is the result of the loss function. If we pass it the values returned by the model and our real Y's. The next step is to optimize our guess. As we are using a gradient tape which tracks our variables, we can differentiate our model W's and our model B's against the loss function to get the gradients for W and B. These gradients give us the direction towards the bottom of the loss curve so that we can generate our next guesses by reassigning W and B within our model to the new value in the direction of the gradient. On our machine learning paradigm diagram, the next step is to repeat. So we now have new W and new B, and so we can make a guess with them and repeat the process. We can see that in a simple code like this, where we will just loop through the training function, we just looked at 50 times. So 50 times we'll make a guess, measure the loss, differentiate to get the gradient of the variables with respect to the loss. Use that to tweak the values in the direction of zero loss, and so on. By the time we are done with our initial W equals 10 and B equals 10, we have changed to something like this, where W is equal to 1.98 and B is equal to negative 0.94. You and I both know the desired values based on the X and Y's that we were given were 2 and negative 1 respectively. So this process has gotten us close. And now, if you want to use this neuron to give us Y from any future X, it will calculate Y equals 1.98X minus 0.94. And so now it's your turn to try this out. You'll next try out some code where you'll see this in action.